Alright children, look at this slide. It looks like a Pink Floyd album cover, right? But it's actually the start of one of the highest scoring chapters in your science paper. Light, reflection and refraction. Now, I know what you're thinking. Oh great, more diagrams and math. But wait, light is literally the reason you can see your crush in the hallway or realize your hair looks interesting in the morning mirror. It's fast, it's trippy, and it loves to break its own rules when it hits a piece of glass. In this chapter, we are going to figure out why swimming pools look shallower than they are, why mirrors make you look lefty, and how a simple piece of glass can turn white light into a party of colors. By the end of these slides, you won't just understand light, you will be able to draw ray diagrams in your sleep, though I would recommend doing them on the exam paper instead. Don't ignore this chapter. Reflection and refraction combined usually carry 7 to 10 marks. It's a gold mine for easy marks if you master the diagrams. Always carry a sharp pencil and a long ruler. In CBSE boards, a messy freehand ray diagram is the fastest way to lose a mark. Neatness counts. Pop quiz. Why can't you find your socks in a pitch black room? Is it because they have gained sentience and are hiding? Sadly, no. It's because of what you see on this slide. Think of the sun as a giant cosmic Wi-Fi router, but instead of data, it's blasting packets of energy, which we call light. Now, look at that apple. It's not just sitting there being delicious, it's actually a professional reflector. When light hits the apple says, I will keep most of these colors, but I'm throwing the red ones back at you. Those reflected rays enter your eye, hit your retina, and your brain goes, aha, an apple, time for a snack. You never actually see an object, you can only see the light that bounced off it. If the light doesn't bounce, you do not see it. This is why ninjas wear black. They are basically trying to be light sponges so nothing reflects back to your eyes. CBSE loves asking for a basic definition. If they ask, what is light? Do not just say, it helps us see. Use the technical term. Light is a form of energy that produces the sensation of sight. That sensation of sight phrase makes examiners very happy. Notice how the arrows in your slide are perfectly straight. Remember this keyword for your answers. Light in a vacuum or air travels in straight lines. Never draw a curvy ray diagram unless you want to see a curvy zero on your paper. Alright, let's talk about the three types of VIP passes light gets when it hits an object. On the left, we have the transparent crew. Think of clean water or your glasses. These materials are like a green light at a traffic signal. Light just zips right through, or as we say in physics, speed, it transmits. No drama, no stopping, just pure clarity. It's why you can see the bottom of a swimming pool and realize it's deeper than it looks, but more on that later. Then, on the right, we have the opaque gap. These are the bouncers of the physics world. This wooden door, it says, thou shalt not pass. Light hits it, gets totally blocked, and what do we get? A shadow. Did you ever notice that shadows are just light deprived zones? They are basically the shape of the object that was too stubborn to let the light through. And do not forget the middle child, translucent materials like butter paper, which lets some light through but make everything look like a blurry 480p YouTube video. The conceptual question is, CBSE might ask why shadows are formed. Always mention rectilinear propagation here. Shadows exist because light travels in straight lines and cannot curve around that wooden door to fill in the space behind it. When writing about transparent objects, use the word transmission. For opaque objects, use absorption or reflection. Using the right verb for light makes your answer paper look like it was written by a pro. You ever wondered why you can see a reflection in a shiny new steel plate but not in your math notebook? It's all about the surface scale. As you can see here, reflection is just light bouncing off a surface. But not all surfaces are created equal. These highly polished surfaces, like the mirror, the calm lake, or that shiny bowl, are the overachievers of physics. They reflect almost all the light that hits them in a very organized way. Think of it like this. If you throw a basketball at a smooth gym floor, it bounces right back to your hand. That is regular reflection. But throw that same ball at a pile of jagged rocks. It's going flying into your neighbor's window. That's diffuse reflection. The secret sauce here is the law of reflection. Light is incredibly disciplined. It always bounces off at the exact same angle it arrived. It's the ultimate what goes around comes around of the universe. The golden rule in your board exam, when you draw a reflection diagram, always draw the normal, that dotted line at 90 degrees through the surface. Students often forget it, but without a normal, you cannot measure the angle of incidence I or the angle of reflection R. And the equal equation. Remember, the simplest math in the syllabus is angle of incidence, that is angle of I is equals to angle R, which is nothing but angle of reflection. If the light hits at 30 degree, it leaves at 30 degree. If the question says light hits a mirror normally at 90 degree to the surface, the angle of incidence is 0, not 90. Do not fall for the trap. Okay, let's talk about light's biggest secret. If you ask a physicist what is light exactly, they might just start sweating. Why? Because light has a double life. On the macro scale, the world of apples, mirrors, and your textbooks, light behaves like a stream of particles. It's like a never-ending barrage of tiny light bullets hitting things and bouncing off in straight lines. This is why shadows have sharp edges. Those light bullets just cannot curve around the apple. But wait, zoom in, like Wayne. On the micro scale, near atoms and tiny slits, light suddenly decides it's a wave. It bends, it ripples, and it overlaps like waves in a pond. It's basically the ultimate chameleon of the universe. It's called the dual nature of light. It's both a particle and a wave. Think of it like a student who is super quiet in class but a total rock star on the weekend. It all depends on the environment. The conceptual edge in this is you mostly deal with ray orbits, the particle side where light travels in straight lines. But if a question asks about the nature of light, mention the quantum theory of light. Remember the term photon? It's the particle that light is made of. Mentioning that light is an electromagnetic wave that does not need a medium to travel will score you those extra effort points with the examiner. Always remember the speed of light in a vacuum. C is equals to 3 into 10 to the power of 8 meter per second. It's the cosmic speed limit. Nothing in the universe is faster than light's particle wave combo. Alright, let's get one thing straight, literally. The most important core concept in this entire chapter is that light travels in straight lines. We call this the ray theory. Think of a ray as an arrow that shows the path light takes. If light were a person, it would be that friend who refuses to take a shortcut through the grass and only walks on the perfectly straight pavement. It does not curve, it does not zigzag, and it definitely does not do loops. Why do we care? Because this stubbornness of light is exactly how we predict where an image will form. Look at the diagram on the right. Those orange lines. Those are rays being disciplined. They hit a surface, they bounce, they pass through a lens, and they meet at a specific point to create an image. Whether it is the shadow of a tree or the selfie you just took, it's all just a billions of straight lines doing exactly what physics told them to do. The mark saver in this chapter, a line is not a ray unless it has an arrowhead. If you draw a perfect ray diagram but forget the little arrows showing the direction of light, the examiner can cut half a mark per diagram. So think arrows is directions which will give you full marks. And when you are differentiating ray and beam, a single line is a ray. A bundle of these lines, like the ones hitting the lens in the slide, is called a beam. If you want to sound like a topper, use the phrase rectilinear propagation of light instead of just saying light travels in a straight line. It is the same thing, but it sounds much fancier in a 3-mark answers. Remember how I just spent the last slide telling you light only travels in straight lines? Well, physics likes to keep us on our toes. Wave theory. Look at this diagram. It looks like ripples in a pond, right? That's because when light hits something incredibly tiny, we are talking microscopic. It stops acting like a straight shooting arrow and starts acting like a wave. See that little gap in the middle? When the light wave tries to squeeze through, it does not just go straight, it bends around the corners and spreads out. This cheating of the straight line rule is called diffraction. There is a reason why, if you look really closely at the shadow of a sharp needle, the edges aren't perfectly crisp. They are slightly blurry. Light is literally sneaking around the edges. You will dive deep into this in grade 11 and 12, but for now, just remember light has a wavy side that it only shows when things get small. So in grade 10 CBSE, you might get a conceptual question. If light travels in a straight line, why are the edges of shadows not perfectly sharp? Your answer should be diffraction or diffraction. Keep this definition in your back pocket. The phenomenon of bending of light around the sharp corners of an opaque object is known as diffraction or diffraction. Don't worry about drawing these wave diagrams for your 10th grade board exam. For your ray diagrams, stick to straight lines. This slide is your expert insight to show the examiner you know the real physics behind the scenes. Okay, take a deep breath. We just saw light acting like a straight shooting particle, and then we saw it acting like a wavy river. Scientists spent centuries arguing about which one was right. It was basically the team Edward versus team Jacob of the 1800s. Then along comes quantum theory to settle the score. Its core concept. Light is neither just a wave nor just a particle. It's a shapeshifter. Think of it like your smartphone. Is it a phone? Is it a camera? Is it a gaming console? It's all of them depending on which app you open. Light is exactly like that. When it's traveling through space, it's a wave. When it hits an atom to create an image, it acts like a packet of energy called photon. This dual nature is a fundamental cheat code of the universe. It explains how light can travel through the vacuum of space where there is no air to wave through and still manage to bounce off your mirror perfectly. It's the best of both worlds. If a 1 mark question asks, which theory reconciles the particle and wave natures of light? Your answer should be the quantum theory of light. Use the phrase dual nature of light. CBSE examiners love the specific term. It shows you understand that light isn't choosing a side, it's living its best life as both. You do not need to solve quantum equations. Just know that this theory exists to explain why light is so weirdly versatile. Alright, let's bring it all together. If light had a social media profile, these would be its 3 different moods depending on who it's hanging out with. First, we have radial. This is a main character of grade 10. When light is dealing with big stuff like mirrors, lenses, or your morning shadow, it's all about those straight lines. It's predictable, it's neat, and it is why your geometry box is about to become your best friend. Then we zoom into the micro world with wave theory. This is where light gets a bit bendy around sharp edges. This is the diffraction zone or diffraction zone. Just remember, when things get tiny, light starts acting like a ripple in a pond. Finally, we have the quantum theory. This is a modern marvel that says, why choose? I have a dual nature. It's the theory that explains how light interacts with the very atoms that make up our world. Basically, for the big stuff and quantum for the really deep stuff. If you see a question about the nature of light, drawing a quick version of this table is a pro move. It shows the examiner you see the scale of physics. For your numericals and ray diagrams, which are the bulk of your marks, stay in the ray theory lane. Do not try to use wave logic to solve a mirror formula problem. Key words to memorize: ray, rectilinear propagation; wave, diffraction or diffraction; quantum, photons are dual nature. You ever played flashlight tag or tried to find your way through a power cut? This slide is the ultimate proof that light is the most disciplined traveler in the universe. Look at that beam. It's not curving to say hi to the shadows. It's not taking a detour. It's a straight, unwavering line. This is what we call straight line propagation. Think about it. If light acted like a spilled glass of water and just flowed everywhere, pointing a torch would be useless. You wouldn't turn it on, and the light would just puddle around your feet while the monster under your bed stayed perfectly hidden. Because light travels in strict straight lines, we can aim it. We can create spotlights, use laser pointers to annoy our cats, and most importantly for you, we can predict exactly where a ray will hit a mirror. It's the predictability of light that makes this whole chapter possible. If the board exam asks, why do we represent light as straight lines in ray diagrams? Your answer should mention rectilinear propagation. It's the property that allows us to use geometry to solve physics problems. Look at the image. The flashlight isn't emitting just one light. It's a collection of them. In an exam, if you are asked to define that flashlight beam, call it a divergent beam because the rays start from a point, the bulb, and spread out as they go. When you start drawing spherical mirrors in the next few slides, remember this flashlight. The rays always start from the object and travel straight until they hit the mirror. No curves allowed. Have you ever looked up at the night sky and thought a star was blinking at you? It's not a secret code from aliens. It's actually just the Earth's atmosphere acting like a giant shaky lens. Look at this diagram. That light from a distant star travels millions of miles through a vacuum perfectly fine. But the moment it hits our atmosphere, bam! It hits an obstacle course. Our air isn't one solid block. It has layers with different temperatures and densities that are constantly moving. As the light passes through these layers, it bends slightly back and forth. This is atmospheric refraction because the air is always shimmering. The light from the tiny distant dot of a star enters your eye from slightly different directions every millisecond. Your brain sees this flickering as twinkling. Basically, the star is sitting perfectly still. It's the air that is drunk. Now, look at the box on the left. Why don't planets twinkle? Think of a star as a tiny single LED bulb far away, a point source. If one tiny ray bends, you notice it immediately. But planets are much closer to Earth. They are like big, bright floodlights, an extended source. Even if the light from one part of the planet bends away, light from another part of the planet bends into your eye to cancel it out. The total amount of light stays steady. Planets are just too big to be bullied by the atmosphere. In your answer, you must use the phrase atmospheric refraction and explain that the apparent position of the star fluctuates. This is a classic 3-mark question. Your answer should have 3 points. Stars are point-sized sources far away. Planets are closer and acts as a collection of point sources, that is extended sources. The fluctuations in light from different points average out to zero, resulting in a steady shine. If the examiner asks why stars appear higher than they actually are, the reason is the same: atmospheric refraction. The light bends towards the normal as it enters the denser atmosphere, making the star look a bit lifted from our perspective. Ever wondered why don't see rainbows every single time it rains? It's because the physics has to be exactly right. Every rainbow is basically a perfectly timed 3-act play happening inside billions of tiny water droplets. First act, the breakup. White sunlight enters the droplet, but here is the thing: white light is a light. It's actually a group of chat of 7 different colors. As soon as it hits the water, it refracts. Refraction means bending. It refracts means bends and disperses. This is the moment the WebGR gang realizes they all travel at different speeds through water and start to split up. Act number 2 is the U-turn. The light hits the back of the droplet, but instead of passing through, it says no and bounces back. This is internal reflection. It is like the back of the raindrop acts as a tiny temporary mirror. Act number 3, the grand exit. The light exits the drop, refracting one last time and spreads out into the beautiful spectrum you see. Did you notice the wavelengths on the slide? Red, that is lambda, approximately 700 nanometers, is the lazy one. It bends the least and stays on top. Violet, lambda, approximately 400 nanometers, is the overachiever. It bends the most and stays at the bottom. This is why red is always the outer arch of the rainbow. If the board asks, explain the formation of a rainbow, you must mention these 3 phenomena in the correct order. First, refraction and dispersion when light enters the drop. Second, internal reflection inside the drop. Third one, refraction when light leaves the drop. Do not forget the environmental mark. To see a rainbow, the sun must be behind you and the rain must be in front of you. If you are asked to draw this, make sure the light enters the top half of the droplet so it can reflect off the back and come out towards the viewer. A tiny mistake in where the ray enters can ruin the whole logic. Alright everyone, welcome to the multiverse of light. Think of light like a video game that changes its graphics based on how much you zoom in. First, we have the macro. This is our home base for grade 10. When light is dealing with big stuff like mirrors, torches, or your face in a selfie, it plays by the rules of ray theory. It travels in straight lines, bounces off surfaces, and is generally a very well behaved student. This is where 90% of your exam marks live. But if you zoom into the micro, things get fuzzy. When light hits tiny gaps, it stops being an arrow and starts acting like a wave. This is wave theory. It's why shadows aren't always perfectly sharp. It's light saying, I'm not just a line, I'm a ripple. Finally, we hit the fundamental level. This is the end game of physics. Here, light reveals its biggest secret, quantum theory. It's a particle and a wave at the same time. It's the ultimate identity crisis, but it's how the entire universe actually works. From your bathroom mirror to the edge of the galaxy, light just adapts to the size of its playground. While this slide is brilliant for understanding the nature of light, remember that for your CBSE ray diagrams, you must stay strictly in the macro, that is ray theory zone. Do not draw wavy lines for a mirror problem. You might get a question like, under what circumstances does the straight line propagation of light appear to fail? The answer should be when an opaque object becomes extremely small, light tends to bend around it instead of traveling in a straight line. This is called diffraction or diffraction. Always use the term dual nature when talking about the fundamental scale. It's the magic word that gets you full marks for theory questions. And that, my friends, is the secret life of light. We started today thinking light was just something we turn on to avoid stabbing our toes in the dark. But now we know better. Light is a disciplined traveler, ray theory, a wavy rebel, wave theory, and a quantum shape shifter, dual nature. It's the reason the sky is blue, why a straw looks broken in a glass of water, and why stars twinkle like they are trying to tell us a secret. But here is a real light bulb moment. Physics isn't just about formulas in a textbook, it's about the mechanics of the universe. Every time you look in a mirror or see a rainbow, you are seeing these laws in action. You aren't just studying science, you are learning how to read the language of the cosmos. Now, go out there, keep your race straight, and let's crush those board exams. And that, ladies and gentlemen, is the bright side of physics. We have traveled at meters per second today, from the way light bounces off an apple to the way it rebels as a wave. We have seen that light isn't just a chapter in a textbook, it is a reason the world isn't a boring dark void. I know. The board exams feel like a giant opaque wall standing in your way right now. But remember, even the thickest wall cannot stop a shadow from forming, and even the smallest crack lets the light in. You have got the concepts, you have got the ray diagrams, and now you have got the physics pro edge. As you head out to study, keep this thought with you. There are two ways of spreading light, to be the candle or the mirror that reflects it. In your exams, I want you to be the mirror. Take all this knowledge, reflect it with perfect precision on that answer sheet, and show the examiner exactly how much you shine. If you ever get stuck on a tricky ray diagram, especially for lenses or curved mirrors, and cannot remember where the rays goes, just remember the normal. Going into a denser medium, bend towards the normal. Going into a rarer medium, bend away from the normal. The mirror mantra. Always check your image characteristics. If it is virtual, it must be erect. If it is real, it must be inward. If you write real and erect in your exam, you are basically telling the examiner you have discovered a new law of physics and they won't give you marks for that. Thank you once again, children.